Alright, hey again everybody. 1,000 pardons about all that. I just downloaded a new version of this little hovercam thing, so hopefully that fixes these recording problems. Not seen as the many curse words that I've uttered in the last hour trying to fix up these videos. So we're going to resume here talking about r squared, which is, we said at the very tail end of that last video, that it's our correlation coefficient squared. How we're going to interpret this is we're going to think about r squared as the proportion of variability in the response that can be explained by our model. And so we'll talk about what that means in a second. We're also just going to note here that since it's the correlation coefficient squared, that means that it's always going to be between 0 and 1, since the correlation coefficient had to be between -1 and 1. And so let's talk about that proportion of variability thing on the top of this next page. And so let's write a couple of examples. And so the first example I'm going to write is a scatter plot where all of the points fall directly on a fitted line. So in this case, if you found r squared, you would find it would be 1. What that means is we can completely explain all of the variability in y with our model. So remember, this idea of variability, y is variable because there are different y values. If y didn't have any variability, then everyone's y value would just be the same. But that's not the case because the y values are different. And so we could explain that variability, we could explain 100% of it with our regression model. On the other hand, if our regression line is perfectly flat, then r squared is going to be 0, which means that even though there's variability in y, we can't explain any of it using our model with x. So this is kind of like completely useless in explaining anything about y. Let's go back to our table of output for this example on page 9. We noted before that we were only going to kind of interpret this stuff little by little. So we've already interpreted these things. And now we're going to interpret r squared, which is found here. Not the adjusted one. We'll get to talking about that, but not quite yet. And so r squared is 0.0352, so you could think of it as either a proportion or a percentage. I'm going to convert it to a percentage in our interpretation and say, okay, 3.5% of the variability in course score is explained by our explanatory variable, which in context of the problem is explained by attractiveness of the professor. You can take a moment to think about, okay, well, it's explaining 3.5% of the variability. What about the remaining 96.5%? So take a second to pause this and just consider what other factors could explain that remaining 96.5% of the variability in course score. All right, did you do it? I'm going to feel real silly if nobody ever pauses. So make sure to pause think about it. Some of the stuff that I came up with, I think the obvious one is how well the professor teaches. So if there were some sort of metric for that, that would hopefully explain a lot of the variability in course score. Some other common ones that arise, what level the class is, meaning that typically introductory courses tend to get lower ratings than more advanced courses. And there could be many reasons for that. Either interest could be one, but there's many other possible other reasons for that. Something we may eventually talk about is gender or race of the professor. So we could discuss some possible issues with bias in these course evaluations. And there are many others that you might think of. Okay, so that wraps up this topic of R squared, which is just kind of how much variability in our response can we explain using this model. In this case, it's not really that much. It's just 3.5%, but as we'll see once we get to the hypothesis test, there could still be a significant relationship between attractiveness and course score. As always, let me know if you have any questions.